This is the final design for the industrial paper roll cradle by Oscar, Aaron, Bree, and Hermione.
Our team was tasked with designing a machine to improve efficiency of a paper roll handling manufacturing lines. Using a reference image, we developed a system that transports large paper rolls from production line to a waiting forklift. The machine lifts each roll in the cradle, rotates at 90 degrees for transfer, then returns to the starting position to repeat the process continuously.
The cradle is rotated using two gears at one end to lower the torque required to rotate the cradle. One of the gears is attached to a lead arm, and the lead arm is connected to a flange nut and lead screw. The lead screw moves the lead arm, which in turn rotates the gears and cradle.
To reduce friction as the cradle rotates, there are two bearings that support the weight of the cradle and hold it in place in relation to the assembly line. We don't know what surface the cradle is mounted to, so the picture to the right may not be an accurate representation of the final system.
We were provided with several requirements that we must adhere to during the design of this system. Firstly, the machine must rotate 90 degrees to deliver the paper within 45 seconds, and then must return back to the start position to pick up another roll within another 45 seconds. The machine is expected to deliver 30 rolls per hour, operate for 2 8-hour shifts each day for 5 days a week, and is expected to operate for 10 years. This is equivalent to 124,800 rolls. All lifetime calculations are done with this in mind. The lead screw should be self-locking so that if power goes out, the cradle does not fall when it is either loaded or unloaded. All components are to be designed with a factor of safety of at least 2. All components required to build a machine are to be commercially available. Finally, we are to design so that we minimize power required by the motor to move the cradle. For the bearing analysis, it was necessary to determine the minimum required load rating to ensure reliability. The selected rating corresponds to a 10% failure rate over the desired service life, meaning that there is a high likelihood that the system will meet its expected lifespan, though this is not guaranteed. The system experiences two primary load conditions. One when the cradle carrying the paper roll rotates to the position the roll for pickup by the forklift, and another when the cradle returns to the start position without the paper roll. Each condition revolves 90 degrees rotation or 1/4 of a full revolution, and both occur an equal number of times over the machine's life cycle. In calculating the bearing loads, it is essential to consider that the combined weight of the cradle and the paper roll is being distributed between two bearings. Using SolidWorks mass properties tool, the cradle's mass was determined to be 74 kilograms. Based on the provided dimensions and density, the paper roll is calculated to have a mass of 911 kilograms. Given that each operation results in only a 90-degree rotation, or 1/4 of a revolution, the machine is expected to undergo approximately 31,200 revolutions over its lifetime. Based on these conditions, the minimum required dynamic load rating for each bearing was calculated to be 1.52 kilonewtons. Bearings meeting this requirements are readily available, including suppliers like MasterCar. The selected bearing was significantly higher load rating of 6,650 pounds, ensuring a large safety margin without incurring substantial additional costs.
During each machine cycle, the cradle rotates a total of 180 degrees, split into 90 degrees lifting the roll and 90 degrees lowering to the start. This motion is achieved by the lead screw displacing the crank arm. The design must be self-locking in case of power failure, and it has to generate enough force to move both the cradle and a 911 kilogram roll. We assumed a crank arm length of 0.3 meters, thread friction of 0.15, collar friction of 0.12, and a single star Acme screw with a 6mm lead. Based on the total combined weight of the cradle and the roll, which is about 984.6 kilograms, we estimated the torque at the lead arm gear to be 3,289 newton meters. Using a 0.3 meter crank arm, this produces an axial force of 10,966 newtons through the lead screw. After accounting for thread and collar friction, the torque required to raise the load comes out to 30 newtons. A self-locking check confirmed that the system will not backdrive under load, and a thread failure check show that the shear stress is only 7.6 MPa, which is well below the steel material limit, so the threads are safe. To achieve the necessary 100-degree crank arm sweep, the linear travel required from the lead screw is around 0.52 meters. Based on our target timing, this corresponds to the required linear velocity of around 0.012 meters per second, which our screw and motor combo can provide. For the setup, we selected a 3/4 inch by 6 Acme screw from McMaster-Carr, which meets all strength and locking requirements. To power the system, we chose a 1 horsepower AC gear motor with a torque output of 47 newton meters at 153 RPM. This motor exceeds our torque requirement and hits a speed close to our target of 150 RPM, making it a solid fit for our design.
For the technical analysis of the bolts in the bolted joint, it was necessary to determine how much preload is needed on the bolt to make sure that the joint didn't separate. From the bearing analysis and the bearing pillow block, it was found that the most suitable bolts would be M16 hex bolts. These bolts would clamp together the bearing pillow block, the support table, and a washer, all of which would be made of steel, and a bolt length of 100 millimeters was also used. As this whole bolted joint is in compression, the preload isn't as important as it would be if the system was in tension, but the suggested preload would be above 10 kilonewtons, as this is the maximum compressive load that would be placed on the bolts. The recommended tightening torque for M16 bolts is around 350 newton meters, and this can be used along with a torque factor of 0.2 to find an initial preload, which was estimated to be around 100 kilonewtons. As this preload is well within the acceptable limits for an M16 bolt, it means that we don't have to worry about the fatigue of the bolt as there are no strong fluctuations in the stress. We considered the factor of safety against joint separation negligible, as these types of bolted joints usually fail in tension, not compression, and the only thing being applied to these bolts is a compressive load. Finally, by looking at the forces being applied to the bolt by the gears, we can conduct a shear analysis on the bolts, and it was found that the shear stress in the bolts does not exceed the maximum allowable shear stress, so the bolts will not fail in shear.
In this gear analysis, we designed Gear 2, the driver gear attached to the lead arm, to be smaller than Gear 3 to create a mechanical advantage, increasing the torque while slightly reducing the speed. For the sake of our initial calculations, assuming ideal efficiency helps isolate the mechanical system's behavior without introducing uncertainties from the motor losses. As previously mentioned, we assumed constant forces, neglected load sharing, and ignored dynamic effects to simplify our analysis. By assuming only one gear tooth pair carries the load, we designed for the worst case scenario, giving us built-in safety margin, ensuring the gears won't fail. Based on material properties of AISI 1045 carbon steel gear, a safe allowable working stress would be 207 megapascals, ensuring long-term durability under cyclic loading. The gears were chosen based on a 10:9 ratio and designed using a module of 6 millimeters and a face width of 60 millimeters. We knew that the shaft diameter was 50 millimeters, which corresponds to a bore size, and we found that two gears, gear 2 being 36 teeth and gear 3 being 40 teeth, worked perfectly for our design in finding the tangential force, the magnitude of the force, and the maximum bending stress to be more than the required factor of safety of 2. The gear ratios were chosen to minimize motor force while limiting flange nut travel. A 0.3 meter lead arm was used to reduce motor load while completing the task within time constraints. All components were designed for continuous exposure to maximum loads, reflecting a conservative approach intended to reduce failure risk and extend component life. Each selected part exceeds a minimum safety factor of 2, providing an added margin to lower the chances of failure and reduce long-term maintenance costs. While a small number of units may still fail prematurely, using higher rated components significantly lowers the overall failure rate compared to cheaper alternatives. This strategy also minimizes downtime and lost productivity. All parts are commercially available, making maintenance and replacement easier and more cost-effective than custom parts. However, some components remain more failure-prone. Gears experience fully reversible loading, increasing fatigue risk, and the bearings limited to 90-degree rotation can develop uneven wear due to repeated stress on the same areas.